Oh yeah, sure.
Okay.
Yeah, so like I mentioned, this presentation is going to be an overview of the internship over the last 4 or 5 months. And I just wanted to say I've had a great time. I've learned a lot, met all of you guys, which was really awesome. And really wanted to thank everyone for making me feel super welcome and helping me out throughout the process and helping me have a great time here. So in terms of the actual internship project, for the first month, I kind of worked on different mini projects that got me introduced to a variety of different ideas. And one idea that I really was interested in was dendritic networks and its applications. I was really interested because it incorporated some of the core ideas of the thousand brains theory, like sparsity, but kind of took it to um, another level in terms of incorporating another aspect of neuroscience, which is the dendritic aspect of it, which I really thought was interesting and I thought could have a lot of applications in a variety of spaces. And my research before Numenta was more focused on reinforcement learning, and I'm really interested in that topic. So I was really curious as to how these two ideas could be combined in a project. Some of my initial ideas were vaguely around having an agent learn like higher level skills in an unsupervised way using dendrites. This sounds vague, and it, like, after reflecting on it for a bit, it was kind of vague. Like, I think I wasn't really clear on what exactly some of the aspects of this were, and there were a lot of open questions on the RL side. So I tried to simplify the problem a little bit, and I thought continual reinforcement learning with dendrites would be a very interesting direction, particularly because Karan and Subutai and now Jeremy are working on that in like a supervised setting. So maybe applying that to a reinforcement learning setting would be interesting. Again, however, continual reinforcement learning is relatively underdeveloped. So like kind of finding a good environment and finding a good problem formulation was kind of difficult based on the literature. And I think finally I landed on multitask reinforcement learning with dendrites, which luckily is related to these last two topics in that it basically involves an agent trying to learn multiple different tasks, except it's a bit easier of a problem to tackle than the last two and more fleshed out because the agent gets access to the tasks and it's much more clear mathematically what the problem statement of multitask reinforcement learning was. So this kind of allowed us to test dendrites in isolation without worrying too much about coming up with a better like reinforcement learning problem. So this last one is like kind of what I landed on. So an overview of the problem statement of multitask RL. So in normal reinforcement learning, you have an agent. The agent interacts with the world. The world, and in this case, with a single task, such as like playing chess or opening a window, for example, is represented by something called a Markov decision process, which basically encodes the rewards the agent receives and also the transition dynamics of the world. So how the world changes. And the goal of the agent is to learn something called a policy to solve the task. And a policy is something that just takes in what the agent observes and outputs the action that the agent takes at every given time. In multitask reinforcement learning, the setup is quite similar, but now we have many different tasks and each task has its own MDP. There's like a fixed set of tasks or a task distribution. So, and during the learning process, the agent kind of gets to see all of the tasks it will encounter. So this is different from like continual learning settings where the tasks are kind of streamed in sequentially and you don't come back to certain tasks. And there's usually a shared structure between the different tasks. So this allows, if there wasn't a shared structure, then the agent would just have to kind of memorize each one or learn each one separately. But because now there's a shared structure, this allows the agent to take advantage of this to perhaps like use one task to aid in the learning of another task. And the goal here is to learn a single policy to solve all the tasks. So it's slightly more challenging than normal reinforcement learning. Yeah, and the policy knows what task to solve. So it's given an ID of the task. And it's a step towards continual reinforcement learning, but it avoids a lot of the kind of underlying challenges, specifically something called non-stationarity. Some of the challenges in multitask RL are, I can go through these kind of quickly. Gradient interference, where the updates for one task could interfere with the updates for a different task, specifically because they have different loss functions, or they induce different loss functions. And another big one is representational capacity, where now you're having one network trying to solve all the tasks, and each task typically has a different type of behavior. So you have to find a way to encode all of this in one network without there being too much interference between different aspects of the network. So again, it's a step towards continual learning, which I guess is like the ultimate goal, but it's an easier problem to solve for sure. And this diagram shows the interference. Like you have one loss for task one and another loss for task two. If you combine them by adding them, you get this combined loss. But if you apply like a gradient descent algorithm to this naively, then you get all these different gradient directions. This red direction is the gradient step you take, and it kind of points off in a nonsensical manner because when you combine the two tasks, they interfere with each other. So the environment in which I decided to test the project out was something called MetaWorld. And this is a robotic manipulation environment where there's 50 different tasks that a robot arm has to do. And all these 50 tasks are shown here. So for example, like turn on a faucet or push an object to a location. And what the agent observes is not it's not like an image. So it's a vector that summarizes where the object is, where the robot arm is, and where the robot arm has to move the object to. So this makes it like a lower dimensional input, which makes the learning a little easier. And then the actions that the agent outputs are the joint torques. So there's, I think, 4 joints here, so it's a 4 degree of freedom. So the torque for each of those joints. And the MetaWorld environment contains 2 multitask benchmarks, one with 10 tasks and one with 50 tasks. So so I guess the specific project in terms of dendrites was how can we use dendritic networks to achieve strong performance in multitask RL? And the hypothesis was that the properties of dendritic networks, specifically the modulating and contextual gating, can be used to mitigate some of the challenges that I mentioned earlier, specifically gradient interference and also representational capacity. And several closely related questions to this was, what is the role of weight and activation sparsity in all of this? And what's important for practical dendritic performance? And what I mean by this is that I guess like in reinforcement learning settings, there's a lot of forward passes and backward passes that need to be done. So like the performance of the dendrites need to be somewhat practical in order to get good training time. So that kind of brings me to the first challenge. That one of the first big challenges in the project was the efficiency of dendrites. So they have a lot more parameters than like standard MLP networks. So for each hidden layer, you have n segments, which takes in an input of c dimensions and outputs in a vector of h dimensions. So it adds this many parameters per hidden layer, which can kind of blow up pretty quickly. And once we realized that the dendrites were pretty slow compared to MLP networks, we did a lot of profiling and realized that there are also several expensive operations, specifically an absolute value and max operation, which chooses the winning segment. And because reinforcement learning has a lot of forward passes to collect data and also a lot of backward passes to learn because it needs a lot of gradient updates, the efficiency of the network can be a bottleneck. So profiling the dendrites revealed some of these slowdowns and several possible optimizations. So a kind of temporary solution which doesn't solve the whole issue that we landed on was using an optimized one segment dendritic MLP. So this does kind of reduce the capabilities of the dendrites because it's one segment, but it does, the trade-off is that it's a lot more computationally efficient because it can avoid this absolute value and max operation and also scale down the number of parameters. In terms of the code base, so yeah, we created a new NuPick embodied code base, and we integrated the dendrites with two existing reinforcement learning code bases. The first is called Garage, and the second is called Soft Modularization. Garage is a more established RL library with strong MetaWorld support. And what I mean by established is that it has like a bigger community behind it, and there's like regular updates and things like that. Whereas Soft Modularization is just a research repo made by a couple of people. But the good thing there is that there's a good baseline to compare to, and the baseline was like the state of the art in the previous version of the environment. The final code base we have now has been integrated with Garage and MetaWorld V2, which is a newer version of MetaWorld, both of which are more stable. We also encountered some challenges with Garage, so we made some modifications to that were made to like suit our needs and to speed up experiments, which were taking like many days in the 50 task scenario, and we recently have been able to like reduce that to at most like 1 or 2 days to get reasonable results, and in most cases like a few hours. So I think, yeah, so the final code base has been integrated with Garage and has been modified to kind of integrate well with NuPick research and NuPick Torch, and also get experimental time down a lot. So
Akash, I have a question.
Yeah.
Just to give me some like a baseline, if there's someone who's running these experiments without the dendritic extension, I mean, would these run in hours? They run in like 1 day, run in minutes? I just kind of, how slowing down did the dendrites make these experiments go?
Yeah, good question. So even with the optimized like one segment dendrite, so those would take around a little less than like twice as long as the MLP networks. So for like, yeah, so if the MLP network would take 1 day, then a similar dendritic network with dendritic segments would take like 2 days.
And just one segment, one dendritic. So it's kind of like almost like linear with the number of segments then.
Yeah.
I mean, if you consider like the base neuron is like one segment, then you can say that, and then you add and the dendrite segment is twice as long, roughly. Something.
I think roughly, yeah.
Okay, thanks.
Yeah. So some of the initial results. So this is with the soft modularization code base and an older version of the environment. And this is with 10 tasks, and the dendritic networks were showing quite a bit of quite good performance. So the left side is the dendritic networks, and we were getting around 80% success rate, which means that on average, 8 out of the 10 tasks were being solved after around 15 million training steps. So that the training steps indicates that 15 million transitions from the environment are collected. Whereas the MLP networks were getting around 40%, 35 to 40% success rate. So this was really promising and kind of validated some of the ideas of the project and some of the potential for dendrites to be applied in this space.
Another question here, Akash. What level of was there any activation sparsity in this experiment, or is this or not?
So this didn't have activation sparsity, but they had weight sparsity, 50% weight sparsity.
So I was trying to understand, this sounds maybe a little weird, but why isn't it 100%? And because the general idea of dendrites should really separate spaces, but if only if the activation is sparse too. So now I think I can understand why you only got 80%. If you had activation sparsity, you might get 100% on this test. So
yeah, so I tried some activation sparsity, but didn't aggressively tune it, and the results were worse. But I think,
yeah, but I would say that's probably not related to the dendrite part. It's probably related to the fact that it's tricky to get, these networks running with activation sparsity.
Yeah, I agree.
Okay.
Yeah, I think with activation sparsity, like from the experiments I ran, I think it's harder to tune, but I think they have a better.
Humans can do many tasks very reliably, right? We don't get confused. And so ultimately, I think a network with activation sparsity and a sufficient number of dendrites should also have achieved very, very high performance. But I think I got it. So but anyway, so far so good. Looks good.
Yeah, and I have some results on the newer environments with activation sparsity in a couple slides. So
also the dendrites should be causing some amount of sparsity as well. I don't know if you looked at that explicitly, although with one segment, it's not going to be that great.
They actually would cause, they would actually cause activation sparsity?
Yeah, because they can turn off neurons themselves.
But there's no enforced sparsity. So
there's no enforced sparsity.
But so okay, that's interesting. Not like a typical biological network where dendrites don't turn off a neuron. But in this case, they actually can turn off a neuron.
They could, yeah.
So then it gets hard for me to understand then. Okay.
Yeah, I think it'd be like a softer version of sparsity where like you would have certain neurons that could be get like close to zero, but not exactly zero.
Yeah.
Whereas some could be like kept multiplied by something closer to 1.
Anyway, again, these are very nice results, although, properly done, not that you didn't do it properly, but in the full implementation of the theories, and we should really have almost 100% success in many tasks.
Yeah.
So, but this is this is sort of an approximation of what the follow-up network would be. That's pretty good.
Yeah. So some of the challenges with the V1 MetaWorld, which is the initial environment design from the developers, was that the reward design was really unstable, meaning the rewards could get on the scale of like many thousands, which kind of causes experiments to crash like this, where you have increasing performance, then suddenly it just drops because the network is dealing with huge losses and just high magnitude numbers, and this can cause like bad grading steps. And with this code base, it also, when we transitioned to the 50 task environment, it also took around 1 week to get this result, which was really bad because in order to see this artifact emerge, it took a week. So
can you explain again what was the cause of that crash? I didn't catch it. What do we have a very high level explanation of that?
Yeah, so I think the hypothesis is that the reward from the environment basically was designed so that the scalar numbers returned were really high. And this, because the rewards are used a lot in the loss functions for the actual neural networks, then like the losses are also super high.
So again, I'm not super familiar with these things. So when you say there's some sort of there's a reward function which says, hey, but for some reason you're saying that number gets very high at some point.
Yeah.
And the reason it gets very high is why? Is it sort of going to some sort of unstable oscillatory regime or thrashing or something like that? I don't understand why that. I don't have an intuitive sense or reinforcement learning network to say why that loss function would get so high.
Right. Well, I think the reward can get high because, well, the reward should get high as you do well on the task. But like a big part of designing an environment is deciding what kind of reward to give. And it can be bad if like the scale of the reward is super, super high. So I guess like a really simple example would be like, if you're playing a chess game and the reward is 1 if you win the game and 0 if you -1 if you lose and 0 if you draw. You could also have a reward that's like 1,000,000 if you win, -1,000,000 if you lose.
But why would that reward function, again, my ignorance, excuse me for my ignorance of reinforcement learning language, but why would that reward function change as you learn? I mean, isn't winning a game always one? Why would it all of a sudden start going up to like 1,000,000? So what would cause it? I have a fundamental lack of understanding of how reinforcement learning works, where that reward function would change. I don't understand that.
The reward function doesn't change.
Oh,
but like as you learn like in this environment, as you get closer to success, you get higher and higher rewards.
Well,
so initially,
again, how do I get higher and higher rewards if the reward function doesn't change? I'm sorry.
Well, because the
reward function sounds like the reward, dude. It must be two different things.
So in this case, correct me if I'm wrong, Akash, but it's not that we have sparse rewards. Like if you win, you get 1. If you lose, you get 0. But we have rewards across the environment, across the task. So if you get closer to the goal, you get a reward.
Yeah.
This is like an aid to the agent. You can think of like.
Yeah. But why would that reward change? I mean, it's like, hey, if you're getting close, it's still 1 to win the game.
Well, it's kind of like, so say you're trying to move an object closer to a goal location. So if you're really far away, you get a reward of 0. If you get a little closer, it's 1. If you get even closer, it's 2. If you get really close, it's like 10. And if you get there, it's like 100.
And that's just a basic function of how reinforcement learning works?
Or that's how the environment is designed. So when you're designing the environment, you have to decide, okay, how is the agent rewarded so that it knows what's good and what's bad.
That's a kind of weird thing. It's like, it seems a little odd to me. It sort of says, like as you get closer and closer to being good at this, you just get hyper, excited or something. It's like, it doesn't seem natural.
Dense rewards is sort of a hack. At least, I mean, the traditional way would be to use sparse rewards, right? So if you win, you get a point. If you lose, you don't get a point. But the state space is huge, so the agent can never find a solution. So what people do in this sort of environments like MetaWorlds, they create these dense rewards. So you give like this intermediate breadcrumbs to guide the agent towards the goal.
Yeah, but you could say, okay, your reward for getting, solving this problem is 10. And then you could have anywhere between 0 and 10 along your way, right? You think the upper limit would be fixed as opposed to, oh, you get 100 or 1,000,000 or something like that. Or maybe it is fixed. It's just a big range. Is that what you're saying? I don't know.
Yeah, I think that was a flaw with this initial.
Yeah, I mean, this is a surprising thing to me. It's like, oh gosh, you see something like this, and it's like, oh damn, what happened? So I'm trying to understand if this is a fundamental issue with dendritic theory, or if it's something else. And I'm hoping it's something else. And what I'm hearing, maybe it is maybe something else.
Yeah, I think it's something else that is like exacerbated by this like bad reward design, which was fixed in this like V2 version, like version 2 of this. And also this kind of.
Oh, it was fixed. Oh, I see.
Yeah,
I didn't let you get there yet. Sorry.
No worries. And this also happens with like this kind of crash after a lot of training steps is fairly common in reinforcement learning, regardless of what kind of network you use, just because like there's the way that algorithms work, there's like the training data kind of changes over time. And when that happens, it can happen.
It seems like a fundamental problem then with reinforcement learning.
Yeah, it's one of the problems.
You certainly don't want to see this.
Yeah. So these kind of challenges motivated us to switch to a version 2 MetaWorld, which had been recently released, and also switch back to the Garage environment, which had a lot more support and seemed like it would just be a good idea to integrate our code base with Garage because it's better built, and we could like build on top of that for our needs, and if we ever want to do different projects in the reinforcement learning space, it would be easy to do those on top of Garage. So these are results with the V2 MetaWorld environment and the Garage code base. V2, the difference is the rewards are on a better scale, like Jeff suggested, and also like some smaller changes And these changes as a whole are meant to make the training process more stable across different experiments. So it's supposed to be a better environment, still capturing the multitask nature of it. This is on the 10 task environment. So I trained a MLP network with hyperparameters given by the developers. And surprisingly, it got 80% success rate on 10 tasks. And just to kind of validate that the dendrite could also do pretty well, I didn't really tune this at all and didn't have activation sparsity. This was just kind of a sanity check. The dendrites got 70% success rate. And the kind of challenge here was that the baseline was already getting 80%. So the room for improvement is much less compared to what we had before. And because like the success rate is a kind of noisy measure of how good the network, how good the agent is doing, it was hard to, it would be hard to find, like clearly determine if a certain method was better than the baseline. So this kind of motivated us to quickly move over to the 50 task scenario where there's likely to be much more.
By the way, before you do that, it's not clear looking at these two charts that actually the tuned baseline was actually better than the untuned dendrites. I mean, if you look at the scales in these charts, I'm not sure if did you numerically verify that? Because if I'm looking at the chart on the left, you know, you'd say, what's the average performance there? I'd say it's around 70% or 75. I'm just curious, was it actually substantially less?
No, I don't think it was substantially less, which is why like I didn't bother tuning this much and move more to the 50 task scenario. The right experiment was just to validate that like nothing major was going wrong.
But it performed worse than previously, where you had about 80%. So.
Yeah, and that could be due to a couple of things, perhaps like not tuning it at all, and also like switching environments can cause like it's a different environment now. So
I'm sorry, and what does KW mean?
K winners.
Okay, K winners.
Yeah. So now with 50 tasks, so these are kind of these are the baseline results. So the left side is what I call a narrow MLP, where the width of each hidden layer is 512 dimensions. And this is the standard network that is being used by the developers and was used in like the release paper for this environment. And it on average got around 45% success rate after 60 million environment steps, which means like 60 million data points were collected throughout training. One thing I was curious about was like, what if we just scale up the baselines? If we just naively increase the capacity of the networks, does performance increase by a lot? And turns out the answer was yes. So just by increasing the width of the hidden layers of the MLP, we were able to get like 70 to 75% success rate on 50 tasks. And this is with like no dendrites. So this was just an interesting observation that I made kind of after this next experiment that I ran, which again, I kind of did the same thing where I had took a narrow meaning 512 dimensional hidden layers dendrites. This one I didn't have K winners just because this was like the first experiment I ran with kind of the most basic addition to the MLP, and did no tuning on this one, whereas this one is more tuned. So this matched the performance of the MLP. So this was more of like, again, a validation on the 50 tasks. And then on the right side, I included, this is after, like, this is the best result after several runs. So this is a much wider network with 2048 units per hidden layer and a K winners of around 0.2. And so 20% of the units are on at every hidden layer. And here the success rate was around 80% and occasionally got up to like 85, closer to 90%.
Is that, I can't remember, is that about equivalent to what the non-dendritic network did with the wide?
This is around like 10%. Or
so the
like
so the wide one on the right here got around to about a little bit less than 70. So
yeah,
we're doing a bit better, but not super amount better. Is that
yeah,
right?
exactly.
Yeah.
And I think
for all of these, are these 50% weight sparsities?
there's no weight sparsity in these. So what the hyperparameters I tuned here are like learning rate, the width of the hidden layers, K-winner level, and did not tune weight sparsity.
Interesting. That's a good observation, because that could make a big difference.
And what was the K-winner level here?
It was like a little less than 0.2. It was like a 0.19 or something.
If you give this
20% on, roughly.
Yeah.
If you give this presentation again, Akash, it would be useful to plot these on the same graph. Use different colors or something like that, because I'm constantly looking at these trying to figure out, because they're basically plotting the same stuff, but your charts are different sizes, and I'm trying to
it's a little hard to compare.
Yeah. So
oh right, yeah.
it would be one big chart with 4 lines of different colors would be better.
Yeah, definitely. Thank
you. And do you know why it dropped suddenly in the middle there for a while? Yeah. Is that just the instability?
Yeah, I think so.
But that doesn't tell me anything. It's like saying it dropped in the middle because it was just bad.
I think, I think that's one of the big problems with like modern reinforcement learning is there's a lot of moving parts. So exactly why that happened is kind of hard to tell. It's probably due to like maybe a bad batch of data being sampled at some point in time that caused some bad gradient steps. But like this also happened on a couple of the MLP experiments that I didn't show in the presentation. So this isn't like unique to the dendritic networks.
So just to be clear, in when you're running these training sets, you're not reiterating over the same data. You're actually looking at different data to kind of approximate the situation. Is that correct?
Yeah, so that's approximately correct. So how in this algorithm it works is you have a buffer of a fixed size. So in this case, 1 million, and you can keep collecting data and adding it to the buffer. And once it gets like over 1 million, then the oldest samples are kicked out and the newest ones are put in. So as you progress through this, the data collected within that buffer changes. And then during gradient updates,
there's a window there. There's a window there that you're moving across, but you're looking at continuously changing inputs. And then when you said you got a bad batch, it meant something that's really off kilter as far as the expectations.
Yeah.
What you've been training up to that point would be.
Yeah, that's pretty correct. So
and within that window, do you do multiple passes of training?
Yeah, so like anytime you do training, you sample like X amount of data from that 1 million and use that for like a batch of gradient updates.
Okay, so as it progresses, it could get trained on the same batch multiple times.
Yeah, it could.
Same set. Yeah.
Like that 1 million is basically like your data set at any given time, but that data set is changing, and then during gradient updates, you're just sampling a batch from that gradient that data set.
Because the data set itself is dependent on your current learning, because because you are interacting with the environment.
Exactly.
So as you learn, the way you interact with the environment changes. So the data, the training data itself will change. Right? That's some of the instability here.
Yeah, and that's like a pretty classic problem in reinforcement learning is like you want to explore a large part of the state space and get like a very wide training data, but also exploit what you've learned so far to be good and get more on that like narrower part. So trading off between
exactly. Yeah.
Again, all these experiments with one dendrite, is that right?
Yeah, this is all with one segment.
Okay.
Did you go, just curious, did you go wider than 2048?
No, I didn't go wider than 2048. I could. These experiments took a little bit longer. Yeah.
Yeah,
Still
just,
reasonable. It took like to get to like 20 million, it took like 10 hours, I think. So and with like 1024 or 512, it only took a few hours. So the experimental time is not bad now.
So I had a question. If within that window, it's a first in, first out policy, there's not any choice being made to retain some training samples for longer than others. It's simply shifting through a set, right?
Yeah, that's correct.
Okay, so if, for instance, there's no article that says this particular training example we want to hold on to for some extemporaneous reason, there's no concept of that.
No, there is no concept of that.
Okay.
There are like several methods in our reinforcement learning that don't do exactly what you mentioned, but kind of prioritize certain samples over others when you're sampling from the buffer. But that we're not using any of that here.
oh, we could, right? I mean, we could implement prioritize replay there. Do you think it would help?
I think it will probably help all of them, but it doesn't really show much in terms of like how dendrites perform on top of other networks.
Okay, yeah, that makes sense.
Yeah.
I just want to make a remark here that this wide networks, we are not controlling for number of params. So when we say wide 2048, that's actually a network 4 times bigger than the one on the left. So that also might be why we're having better results. It's not just because it's wide.
Yeah, that's why I think it's useful to have all the charts together one after the other, because it would be useful to compare the wide MLP against the wide dendritic network. Just as an example.
Oh, yeah. And we are running the 2048. We are actually running 4 variations. So there is with weight sparsity, with activation sparsity, just MLP, and with both, and just dendrites.
Yeah, just dendrites. No sparsity.
Yeah, we can show all 4 of them in the same chart. That's going to be easier to look at.
Just so I understand what you just said, when you make the network wide, you're also making it deep as well. That's implied.
No, we are not making it deeper, but we have more params, right? All layers are like 4 times bigger.
Oh, okay. So you're just scaling it up, but you're not conserving the number of parameters. Okay, I got it.
Yeah, exactly.
The depth
is there a
here
way
is
to
all
get
3. There's 3.
A couple of sorry.
Go ahead.
Yeah, a couple of things. Is there a way to get like a summary number for each of these charts? I know it's very noisy and stuff. Could we say that is there a way to extract like the mean of the last few million iterations or something like that to say, okay, the network on the right was at about 81%. The network on the left was at about 43%, whatever that, something like that, so that you can put it in a table and you can look at, in a succinct format.
There are ways to do that. So I think like typically how it's done is something like you mentioned, where you have like you look at the last X amount of training steps and you take the median over those or the mean over those. So some sort of statistic.
Yeah,
and that's pretty common in reinforcement learning.
And the other question I had, do you think the network has converged, the one on the right? Looks like it might still be going higher.
No, I don't think it's converged.
Okay, is it still running?
This one, no. I stopped it to run a couple other experiments because, but I mean, I think I could resume it.
Okay, that's it's interesting that it could keep going higher.
That's a good observation.
So I think several next steps in terms of experiments. I think at a high level, it involves just experimenting with different configurations of dendrites. So one thing is incorporating multiple segments and weight sparsity. I think weight sparsity could help, and also it could be a good way to keep the number of trainable parameters somewhat fixed, even as we scale up other aspects of the network, like adding multiple segments or even more hidden layers or widening the hidden layers. And like if we increase the weight sparsity for every kind of aspect added, then the number of parameters could say the growth in the number of parameters can be controlled. which is kind of the third bullet point as well. And I think a big part of this is also adding to the code base different statistics to track the properties of dendrites. So some of these were things like the mutual information statistic that I've discussed in like past meetings before, where each, like the modulation from each segment is treated as like a random variable between 0 and 1, and tracking the entropy and mutual information there. Some of these statistics are not incorporated into Garage yet. So adding those, I think, to analyze the properties of the network would be useful.
Unfortunately, I have to step out now. That was, I'm not sure if you're almost done, but it was very nice. And I think it's, we're sure. I mean, again, I would like, the only thing I'd like to emphasize here is that we should be able to get 100% of these tasks eventually, but you have to implement all these things. And anyway, I thought that was pretty cool. Yeah, I have to say goodbye. So,
yeah, this is the last slide, so perfect timing.
Good. Well, I'm gonna leave right now.
Yeah, Akash, that was a great job. Thank you. Yeah, so you're doing a write-up right now. If we kind of step back, like, how do you feel intuitively now that you worked on it for a while? What is your overall sense of the promise of this kind of direction?
I think it's definitely promising because I think it's a different test bed for the dendrites. I think, yeah, like getting, like Jeff mentioned, as close to 100% as possible is possible with the dendrites. And I think showing that like the way dendrites add parameters to networks is a effective way of doing it will be possible with this project. Kind of similar to like transformers, in that like transformers have a huge number of parameters, but the way they add the parameters is like really particular and achieves really good performance. So like showing something similar where we have a lot of parameters, but the way we've added those parameters is really specific and inspired by really specific ideas, and they work really well. That can be done in this project, and I think like we're getting there. And I think the environment can be extended to more difficult benchmarks pretty readily. So like I shared on the Slack recently that some people have created a continual learning version of MetaWorld. So it uses the same base environment. It just changes the way the agent sees the tasks and adapts it to a continual learning setting. So I think that could be like a good next step. So I think there's a lot of promise in that direction as well.
Yeah, yeah. Well, that's good. Yeah, the multitask one is also, just like your motivation earlier, is also a good test bed for dendrites. It's same underlying intuitions apply, but a very different kind of formalism than continual learning.
Mm-hmm.
But the concepts of avoiding gradient interference and so on are still apply.
Yeah.
Do you think these are publishable results now that you've got 50 task results? Or
I think they're close. We definitely have to like run it on multiple seeds and then do like ablation studies and things like that. But I think in terms of main results, they're close. And I think like this is like the lower bound because the tuning, like this is with some tuning, but there's a lot more tuning to be done, especially with these.
Mm-hmm.
So I think, yeah, like it's probably publishable now and definitely will be soon with like incorporating these and properly tuning. I think like one thing I noticed in this project is like, I think the tuning is a little bit tricky, especially with things with K-winner activation sparsity. Like it's a little bit finicky. So like finding the right configuration can really, like once you find that right pattern, it can really get great performance.
Yeah. And did you have boosting turned? Did you have boosting turned on or off?
Off for the dendrite,
yeah.
Dendrites, because I think like the dendrites do that, or should be doing that.
Kind of, yeah. They don't have the same pressure though. But the with boosting, one of the big issues I think is just that the duty cycle window is just so short here. you know, compared to the duration of a task.
Yeah.
So that's an issue.
Do you have an idea of how much of the compute power goes into that max operations? Like if you remove those max operations and keep the same level of sparsity that is induced by those max operation, how much efficiency or speed do you think you can gain?
So I'm not really sure what the answer would be to the second part of the question, is like if you remove the max but keep the sparsity.
Like if you have a way to keep this about the same level of sparsity but not having that max operation.
Right. I think we have we had profiling numbers for the impact of the max that I don't remember off the top of my head, but if I pull up the Google Sheets for, we should have that.
Okay.
Lucas or Subutai, do you remember approximately?
I didn't get Jeremy's question actually. So can you please repeat it?
So if I understand correctly, Akash said that the max operations are very computationally expensive and slow down the whole simulation and getting that the info through the network. So the idea is, if you find a way to keep the same level of sparsity that is induced by using that k-winner without using that k-winner strategy, how much of an improvement in computation, how much speed and how much of your computation speed can be improved by that?
Well, but the max is not coming from the k-winner. The max is coming from the dendritic activations.
Yeah.
It could. So yeah, the max is taking a big toll. So the fact that I'm not sure the exact number is now, but I think it was like 3 or 4x slower. And it's not just about being a max. Any operation that you do to consolidate the dendrites, and we tried like a few, there is an impact. And yeah, it was about like
so you mean if instead of a max you have a linear operation, that would be about the same computational power, right?
Oh yeah. If you have a linear operations, then that would solve it.
But we tried summing across the dendrites, right, Lucas, and it was similar. If you sum it afterwards, it's similar. Yeah, any operation you do, if you break it down into 2 operations, then you have that slowdown. We've tried different versions that didn't break it down into 2 operations, but they're not true to what we want to do with dendrites, right? So we want that max, we want that, winner take all operation there. It would solve, but I don't know how we can get rid of it.
Yeah, we've been talking a little bit with Karen about that, but we might need to do some more exploring about a solution to that.
Yeah, but the short
answer,
answer,
we have a whole bunch of we had a whole bunch of results from the profiling we did earlier. I think all the answers are in that. It's in a Slack channel somewhere.
Okay. It's in a Slack and like a Google Sheet. I can share that with you, Jeremy.
Can you send me the link? That would, otherwise I can go get it. But
I'll add Jeremy to the channel as well. And yeah, Jeremy, if you can like go on the channel, we discuss that.
Sounds good. Thanks.
On a kind of unrelated note, like I think the results that like Karan, Jeremy, and Tubutai, you guys got on the continual learning, the like improvement over like XDG. I am curious to like see how well like a naive like MLP network with a similar number of parameters would do in that scenario, just to see like the impact of just raw like representational capacity.
Oh, it would do horribly. On continual learning, all MLPs, just standard MLPs, will get chance accuracy.
Okay.
Or basically we'll just learn the last thing.
Okay, yeah. That would make sense.
It doesn't matter how big it is.
Got it.
So there we're a little bit better off. We don't have to worry so much about the number of parameters. It's more about just getting the accuracies high enough.
Yeah, here I think this is one of the big challenges here is that like I think any network, if you just scale up the number of parameters because it's seeing all the data, can keep doing better.
Exactly.
Or
Yeah.
there's probably a point of diminishing return because it's just hard to train big networks. But yeah, like I think getting good results with the control and the number of parameters is like the challenge in this project.
Yeah. Yeah, exactly. I think if you took a dense network that had the same number of parameters as your wide dendritic network, it might do quite well.
Yeah. And yeah, like that's kind of validated by this wide MLP. It has slightly less parameters than the dendritic.
Yeah.
So a question like on implement different statistics into Garage, like are you contributing to the Garage code base or our copy of it?
So all the changes we made to Garage are basically like subclassing different different classes in Garage and doing the relevant changes. We haven't contributed anything directly to Garage.
So if you want to upgrade those things, we have to incorporate all that again. If
like
Garage has a new version, we're gonna have to make sure like everything is.
Yeah, but for this project, we are sticking with Garage. In the long run, I believe there are better alternatives. Facebook just released reinforcement learning library that's fully compatible with PyTorch. So that's I don't want to contribute back to Garage, although we subclass when we need it. We're like recreating some of the things we needed, but in the long run, I don't think we're gonna stick with Garage. So.
But still Garage using our own copy.
Yeah, we are kind of using our own copy, and I'm modifying a lot of things as well. So we have like a half Garage, half our code base, but always like subclassing and changing only the things we need. We're not having our own, modifying our own fork of Garage. That's what you're asking.
Yeah, no, I'm asking like if do we have to, you know, they have new version. There's a new paper out there, and there's a new version of Garage. Do we need to keep up all those modifications?
I think for the most part, no, because most of their algorithms are fixed. Like they've already implemented them correctly. So like I think, yeah, there's no real pressure to keep up.
Yeah, only if you keep using it and like using new stuff. But yeah, like I said, I don't think that's gonna be the case.
What's the Facebook library called?
I don't remember the name. They released it, I think, last week or 2 weeks ago. I can send it to you later.
Yeah, sure. Yeah, I wasn't aware of that one.